Welcome to the second lecture of week 2 in network analysis. Today we'll see how to use mesh analysis and the knowledge of differential equations and inductor and capacitor properties as applicable to DC circuit transient analysis for analyzing the behavior of a circuit. This will this lecture will tell us how to uh, utilize all the knowledge that we have related to circuit analysis to solve complicated problems. Like for example, in this circuit given in the figure, we're trying to use mesh analysis to find out the circuit behavior. And we have labeled the mesh currents. This is I1t, this is I2t. You have an inductor, 1 Henry inductor, a resistor 0.5 ohms, 2 ohms resistor, a capacitor half farads, and then you have two sources. The switch is thrown from 1 to 2 at t is equal to 0. So initially the circuit is connected to the 2-volt source, and then at t is equal to 0 it is suddenly connected to the 3-volt source. And prior to t is equal to 0 the circuit is in steady state. So when it is connected to the 2-volt source, the circuit has already achieved steady state. So the way we solve the problem is going to be very similar to what we have done before. The only difference is that we'll see how to combine the methods that we have learned in the past few lectures with the methods of that we have learned earlier in the first semester, like mesh analysis and nodal analysis. So today we will talk about an illustrative example related to mesh analysis. So what we do in mesh analysis, the first thing that we do is we label the mesh currents, and then we write down the equations for the two meshes. So in this case, since we have an inductor and a capacitor, the equations will not be algebraic equations, they'll be differential equations. So this is how you write. You start your equation for this mesh. You start from this point. For example, this is a voltage rise, so this is minus 3 plus L di by dt, and these equations we are writing, please remember, we are writing them for t greater than 0 because we are interested in the circuit behavior at t greater than 0. We want to find I1t and I2t as functions of time for t greater than 0. So for t greater than 0, this switch would be connected to point 2, and these two meshes would be in place. This source would be out of the picture. So this is minus 3 plus LdI by dt plus I1 minus I2 into 0.5. That's what we are writing. L is 1, so instead of di by dt I'm writing I1 dash t. Similarly for the second mesh, I start from this point. This is zero point 0.5 in the direction of the mesh current. 0.5, the current in this is I2 minus I1, I2 minus I1t, and then plus VCT, VCT is a drop, plus I2t into 2 ohms. And now this VCT, the whole drop across the capacitor, can be broken down into this integral plus this initial voltage as we have seen before. So this is Vc0 plus twice integral of 0 plus to t I to t dt. This whole thing is Vct. So these are the two differential equations that we get out of the circuit by using mesh analysis. We can convert the first one is a pure differential equation, the second is an integral differential equation. So we'll convert the second equation also into a differential equation by integrating throughout, by differentiating throughout. So when we do that, we'll get for the second equation, once you differentiate throughout, we'll get 0.5 I2 dash t minus I1 dash t plus the differential of this is going to be 0 plus the differential of this plus twice I2t, and then plus twice I2 dash t equal to 0. So the first equation is here and the second equation is here. Now we'll just write them in a more compact form. Both of them, we write it like this. The first equation, I1 dash t plus 0.5 I1t minus 0.5 I2t is equal to 3, and the second equation write as minus 0.5 I1 dash t plus 2.5 I2 dash t is 2 and this 0.5, and then plus twice I2t equal to 0. So writing this using the differential operator p, you can write p plus 0.5 minus 0.5 and then minus 0.5p and then 2.5p plus 2, and here you have I1t I2t is equal to 3 and 0. So once you have written this, it is very clear that you have reduced the circuit behavior after t greater than 0 to a differential equation form. So you know clearly now that the circuit, how the circuit is going to behave. But to solve the differential equation, you need to find the initial conditions for both the currents. You need to find initial condition for I1t. You need to find the initial condition for I2t, in the sense that you need I1 0 plus, you need I1 dash 0 plus, and you need I2 0 plus and I2 dash 0 plus. So these initial conditions are required in order to solve the set of differential equation system that we have up here. So what are the initial conditions? Let us first see what is I1 0 minus. I1 0 minus you'll get because this whole thing is in steady state before the switch is thrown to 2. So when it is in steady state, it means that this inductor will behave like a short circuit. This capacitor would be like an open circuit. So all the current is going to flow like this through this this is the first loop, and there is no current going to flow. No current is going to flow across like this. So I1 0 minus, you can say, is simply 2 divided by 0.5, that is 4 amperes. And similarly, you can say Vc 0 minus, the voltage across the capacitor, is going to be the voltage that is applied here, because there is no current across. So this point is connected to this point here, and similarly the potential of this point and this point is equal to the potential of this point. So Vc 0 minus is going to be the source voltage, that is 2 volts. So from this information, you know that this implies that I1 0 plus is going to be 4 and Vc 0 plus is going to be 2, and this is because the inductor current and the capacitor voltage are going to be continuous, because there is no impulse in the source, as we have seen in detail before. So with this information, we need to find I2 0 plus also, and also the derivatives inductor. The other three initial conditions we need to find out by using the relationship that we have for I1 0 plus and Vc 0 plus. So let us try to do that. Let us write down the first differential equation for the 0 plus condition. So you have I1 0 plus 0.5, this is I1 dash, I1 0 plus minus 0.5 I2 0 plus is equal to 3. We have I1 0 plus, so you can simplify this, we get I1 dash 0 plus minus 0.5 I2 0 plus is equal to 3 minus 0.5 I1 0 plus. I1 0 plus is already given, it's 4, so it is 3 minus 0.5 into 4, that is 3 minus 2, that is 1. So this is one equation that we get. Please remember that these are unknowns. I1 dash 0 plus is not known, we need to find it. I2 0 plus is not known, we need to find it. Now let us see the second equation. Uh, since we know the capacitor voltage at 0 plus, let us try to use this information to in a way simplify the whole thing. So we can combine the two differential equations by writing the mesh equation for the bigger mesh outside, and this would help us in solving the problem slightly more easily. So let us write down the mesh equation for the outside mesh at 0 plus. That is basically combining the two equations together and then putting t is equal to 0 plus condition. So when we do that, we'll get minus 3 plus I1 dash 0 plus, which is the first part of the first mesh equation, and then we proceed ahead, and then we write the condition of the capacitor voltage at 0 plus, which is 2 volts plus 2, because VC 0 plus is 2, and then let us come down, plus 2 into I2 0 plus is equal to 0. This we get from the inside, that since we already have an equation which has I1 dash and I2, we can get a similar equation which has I1 dash and I2 if we write down the mesh equation for the outside mesh at t is equal to 0 plus. So this gives us I1 dash 0 plus plus 2 I2 0 plus is equal to minus 3 plus 2. On the right hand side it gives us 1. So now we can subtract the two equations, and because both of them have only two variables, so when you subtract the two equations, on the left hand side you get 2.5 I2 0 plus, these two will cancel out, and on the right hand side you'll get 0. So this tells us that I2 0 plus is 0, and this also tells us that I1 dash 0 plus is 1. So this gives us another other two conditions, the condition of I2 0 plus, the condition of I2 dash 0 plus, and we have already found out the condition. No, we need to find I1 dash 0 plus. So I1 dash, no, I1 dash 0 plus we found. I2 dash 0 plus we need to find. We can find it by putting all these conditions in the second equation. So when we do that, you get minus 0.5 into I1 dash 0 plus plus 2.5 into I2 dash 0 plus I2 dash 0 plus plus 2 I2 0 plus, which is 0, plus 0 is equal to 0. So this which was to be found out, I2 dash 0 plus, is just I2 dash 0 plus. This is 0.5 into I1 0 plus divided by 2.5 I1 dash 0 plus, and I1 dash 0 plus we have already seen it is 1, so it is 0.5 into 1 divided by 2.5, which is 0.2. So this I2 dash 0 plus is also found. So you get the four initial conditions basically from two initial conditions only, I1 0 plus and VC 0 plus. This is the approach that has to be followed throughout. So let me write down the initial conditions. So I1 0 plus, we have seen is 4. I1 dash 0 plus we have seen here it is 1. I2 0 plus we have seen it is 0, and I2 dash 0 plus we have seen it is 0.2. So these are the 4 initial conditions, and this is all the information that we need to solve the differential equations. So we have written down the differential equations for the two mesh currents. We have found out the initial conditions for the two mesh currents. Now we just need to put in the knowledge of differential equations as we know to finally write down the equation for the final differential equation, final equation solution for the system. Before we do that, we know that in the solution of both the differential equations will contain a particular integral and a complementary function, because this is a non-homogeneous system of equation. The particular integral for both I1t, if we denote it by I1t hash, and I2t, I2t hash, where hash denotes the particular integral, can be found out by looking at the steady state values of the current I1 and I2. As we have seen before, we can do it by assuming the form of the particular integral similar to the form of the forcing function. So particular integral is going to be constant because the forcing function is constant, and then we can put in that here. That will also give us the result. The other way to find the answer is to find the steady state values of the currents flowing in the circuit. So when this is connected to 2 for a long time, what is going to happen is that this inductor is going to be a short circuit, behave like a short circuit after a long time. So this current is going to be 6 amperes, and this current is going to be 0 because this is going to be an open circuit. So you can say this is 6 and this is 0. So these are the particular integrals. This is one way of doing it. The other way of doing it is to assume a constant value a, another value b, and then put in those values here. So you'll get 0.5 a minus 0.5 b is equal to 3, and then you'll get twice b is equal to 0, so b is 0, so this current is going to be 0, and this 0.5 a minus 0 is equal to 3, so a is equal to 6. So you'll again get the same thing. So whether you find the steady state current or you assume you use the method of undetermined coefficients, particular integral can be found very easily. Now the next thing is to write down the value I1t and I2t in terms of I1 star t, which is the complementary function, plus I1 hash t, which is the particular integral, and then put in the values for the uh, of the initial conditions to find the constants. So I've already written down separately the form of the complementary function, which you can get very easily by looking at the determinant and then seeing what are the roots. So I'll just write down the solution for the complementary function and then the complete equation. So there are two roots for the system. You get a root at p is equal to minus 1 and another root at p is equal to 0.6, so minus 0.6 from this. So you can write down this k1 e to the power minus t plus k2 e to the power minus 0.6t plus the particular integral, which is 6, and similarly you can write down for I2t k3 e to the power minus t plus k4 e to the power minus 0.6t plus 0, because the particular integral is 0. So these are the two equations that you'll get finally, and this is very simple because you know how to find the complementary function for this determinant. for this, for the homogeneous counterpart here. So this gives us the two equations. Then what is left is to substitute the values of the initial conditions into these two equations to get the values of k1, k2, k3 and k4. So if you do that, you'll see that I1t is 0.5 e to the power minus t minus 2.5 e to the power minus 0.6 t plus 6, and I2t is minus 0.5 e to the power minus t plus 0.5 e to the power minus 0.6 t. So these are the two equations, two mesh equations for t greater than 0, and the problem is solved. So we have seen how to use what we already know of circuit analysis, that is mesh analysis, in combination with our knowledge of differential equation that we have learned here, and our knowledge of the inductor and capacitor characteristics that we have learned in these lectures, to finally solve the circuit and get the complete response of the mesh currents as the uh, time proceeds, in the sense that we get the complete transient plus steady state response. This is the approach that we have to follow, irrespective of whether we are solving a circuit through mesh analysis, nodal analysis, or we are using any theorem to solve the circuit. Although I'll not completely solve this problem of a coupled circuit, which can be solved in methods similar to the ones that we have adopted before. What we have here is a transformer which is connected to a DC source at time t is equal to 0. The self-inductance of the primary winding is 1 Henry, of the secondary winding it's 4 Henry, and the mutual inductance is 1 Henry. Let us label the two mesh currents as I1 and I2, and we can assume that initially there was no current in the circuit, so I1 0 minus is 0 and I2 0 minus is also 0, and this is also the case for I1 0 plus, because of continuity of the inductor current. There are inductors in the primary side and the secondary side, and there are no impulses. So two initial conditions we already have. We want to see the profile of the currents I1t and I2t for t greater than 0, that is to say after the switch has been closed. The method is similar, the approach is similar. We'll write down the differential equations for the uh, primary side. For t greater than 0, we can write down minus 5 plus 1 into I1 dash t. No, this is I1t because this is the resistance. 1 into I1t plus another 1 into I1 dash t, plus because of the mutual inductance, the current I1t is flowing into the dot and the current I2t is flowing out of the dot. So as you know, the sign convention says that this means that the mutual inductance is going to be negative, because one is flowing into the dot, the other is flowing outside the dot. So you'll write minus 4 times the mutual inductance I2 dash t is equal to 0. This is the first equation. Let us write it more simply. So it's going to be I1 dash t plus I1t minus 4 I2 dash t is equal to 5. This is the first equation. The second equation is here, minus 4 in the second mesh, I1 dash t, the mutual inductance part, plus 4 I2 dash t, the self inductance part, plus I2t is equal to 0. So you can write down the differential equations using the differential operator p like this, 5 0. So you have minus 4p, sorry, you have for the first equation For the first equation you have p plus 1 minus 4p, and for the second equation you have minus 4p and then 4p plus 1. I1t I2t is equal to 50. So this is the differential equation set for the circuit. The next thing is to find out the uh, the initial conditions. We already have I1 0 plus and I2 0 plus. We need I1 dash 0 plus and I2 dash 0 plus, which we'll get straight away from the two equations. If you substitute at 0 plus for the first equation, you can write I1 dash 0 plus I1 0 plus minus 4 I2 dash 0 plus is equal to 5. So you know I1 0 plus, it is 0. So you can write I1 dash 0 plus minus 4 I2 dash 0 plus is equal to 5. This is one equation. The second equation you get here, minus 4 I1 dash 0 plus 4 I2 dash 0 plus. This is going to be 0. It's 0. So minus 4 I1 dash 0 plus 4 I2 dash 0 plus is equal to 0. So these two equations will give us the values for I1 dash 0 plus and I2 dash 0 plus. So we have the differential equation system, and we have the initial conditions. So the pattern of the problem is similar. After this you have to see the complementary function for uh, for the differential equation system that you have, the simultaneous differential equations that we have here, and then from the complementary function uh, and the particular integral, I'll write down the complementary function straight away, and then you have to apply the initial conditions to find out the values. So if you see the determinant of this matrix here, it will give you two roots. The characteristic equation will give you two roots. One is p is equal to minus 0.23, the other is p is equal to minus 1.43, and the particular integral, if you see, the steady state value of the current here is going to be 5 amperes. So I1t hash, the particular integral, is 5 amperes, and the steady state value for the current here is going to be 0 because there is no voltage source connected. So I2t hash is going to be 0. There's going to be no di by dt, so there is no mutual inductance, so there is no voltage source connected, so the particular integral is going to be 0. So you can straight away write down the values. I1t is equal to k1 e to the power minus 0.23t plus k2 e to the power minus 1.43t plus 5, and I2t is equal to k3 e to the power minus 0.23t plus k4 e to the power minus 1.43t plus 0. So these are the two differential equations that we have, and these are the four initial conditions that we have. Put in the initial conditions into these two, not the differential equations, the two solutions that we have. Put in the initial conditions into the solution and try find the values of k1, k2, k3 and k4, and hence the problem is solved. So this is the approach that is followed throughout in all kinds of questions. The only trick lies in trying to find out the initial conditions, which is slightly tricky because we have to, like in the previous example, you have to take the voltage across the capacitor and try to find out the other initial conditions from it. So this is all for the second week. We'll gain expertise in solving these problems only if we practice them a lot. So there is a worksheet that is also attached to this presentation. I expect all of us to try to solve those problems and to come up with any difficulties if they are faced. Thank you very much.